Hello, my name is Sanket, and I will be presenting our paper, Learning Surrogate Loss Functions for Predict and Optimize Problems. This is joint work with Kai, Brian, Andrew, and Milan. Jumping right into it. What are predict and optimize problems? Predict and optimize is a framework for making decisions using machine learning. So specifically, first you do predict, right? You build a machine learning system which can, given features, make predictions about what the labels should be. And you train this on some sort of intermediate loss, and then you get a predictive model. And then, right, which is rather specific to predict and optimize, you take these predictions and you use them in a very specific way to make decisions. Specifically, you take these predictions and use them as parameters in an optimization problem, such that once you solve this optimization problem, it will give you which decisions you should take, and then you can evaluate these decisions and you can get the decision quality. So predict and optimize is this framework for you first predict and then use these predictions as parameters in an optimization problem to make decisions, right? Just to make this concrete, we have this budget allocation problem from a AAAI 19 paper by Wilder et al. Specifically, what we do is we take features, right, which are essentially information about websites. And based on those features, the predictions that we're trying to make is what's the click-through rate, or what's the probability that a fixed set of users is going to click on this ad on this website, right? So per user, per website, what is the probability of clicking? And then how you use these predictions, like, so you get a matrix of predictions. And then how do you use these predictions? You solve an optimization problem to choose a subset of W websites from like this overall space of websites such that you maximize the expected number of people that actually see the advertisement, right? There's a slightly complicated formula, but that's all we're trying to do. And the question that sort of like predict and optimize or smart predict and optimize or decision focused learning is asking is, if we know that our predictions are going to be used in this very specific way for this very specific purpose, can we tailor our predictive models for this specific task, right? So this is the high level pitch of predict and optimize problems. And how do people do this smart predict and optimize or decision focused learning? So the state of the art is to take these two halves, predict and optimize, and sort of push them together into an end-to-end pipeline, right? So then you have everything, we have predict and then optimize. And then the way to sort of learn a predictive model is to pass the gradients end to end from the decision quality all the way through the decisions to the predicted parameters, right? And what a lot of papers have shown is that for certain kinds of problems, this is a good idea, right? You can do better by taking into account task-specific information. Now, what's the challenge? To sort of like better understand the challenge, we sort of have to better first understand what decision quality means. The way that people measure decision quality in this predict and optimize problems is, given a decision made on predicted sort of parameters, how well does this decision do on true parameters? So just sort of taking a step back, what does this mean in terms of the budget allocation problem? Maybe it's complicated there. We're taking a very simplified version of the budget allocation problem where you have two websites, 1 and 2, and you have to pick which website to advertise on. Website 1 gives you utility 1, website 2 gives you utility 2. So now if you correctly predict this, then you will say, pick website 2, and that will give you a true utility of 2. Say you make the prediction 2 and 1, right? Then what you're going to do is website 1 is the one you're going to pick. And then because that thing's true utility is 1, you're going to get 1. But the issue here is that even if you make the decision 1, 2000 and not 1, 2, you still decide that like I should pick website 2, right? And so in some sense, this decision quality, this is not providing a lot of information. And so if you wanted to train a model based on this decision quality, it would have very uninformative gradients, right? Like it doesn't tell you how to improve your model because it's piecewise constant. And this is an issue. And this is an issue that's well known. And the way that past papers have sort of gotten around this is that they've looked really hard at the optimization problem. And they've said, you know what, instead of like having a piecewise constant thing like this, you want to smoothly interpolate between these two. But all of the papers sort of handcraft these loss functions, and the more complicated the problem, the more sort of like ingenuity it needs. And so it's really hard to sort of take it and deploy it in the real world. In addition, a lot of the surrogates that people come up with are not convex. And so if you're optimizing like predictive models using these surrogates, you'll often get stuck in local optima and you won't find the best function. So in this paper, our contribution is, can we learn surrogate loss functions, such that like automatically, such that you don't have to put in any sort of like intellectual effort into figuring out what is the best surrogate. You can just learn one right off the bat for any predict and optimized problem. How do we do this? This is sort of like our approach. And this is the pipeline for decision-focused learning. And if you stare at it really hard, or maybe not that hard, what you'll see is that it kind of looks like a supervised learning problem, where the decision quality can be a decision-making plus decision quality can be sort of like abstracted out as a decision loss, right? Now, this decision loss isn't good. Abstracting it like this doesn't change the problems associated with decision quality having non-smooth surfaces and gradients not being informative. But what if we could learn a surrogate loss that was convex by construction, but also behaved like the decision loss, right? Then it would be easy to optimize over that. It would provide informative gradients, but also it would sort of take into account task-specific information, right? And so the way that we do this, we learn a good surrogate loss, is that we first create a data set. So like the inputs are predicted parameters and true parameters, and the output is decision quality. So you create a data set of predicted parameters, true parameters, and decision quality. And then you fit a convex model to this data set, right? And what you get is a surrogate loss that is convex by construction, but also sort of has a realistic y hat comma y to dq mapping. Okay. How do you generate these realistic inputs? It's not clear. The assumption that we use in this paper is that a predictive model will get you close to the true parameters, but the real job that the decision loss has to do is differentiate between these 2 points that are close to the true parameters, but not exactly the true parameters. So in the context of our example, what this means is, on the left-hand side is the true labels, and then on the right-hand side are two predictions, possible predictions, right? And which one is better and which one is worse is the question that the decision loss has to answer, right? So consider adding point 1 to user 2 website B, or point 1 to user 2 website C, right? In MSE space, both of these are errors of 0.1 or 0.1 squared, 0.01, and so there's no difference, right? But if you actually look at it, right? If you add 0.1 to website B, it doesn't actually change the decision, because website B is not something that users 1 and 2 frequent. So you'd never choose website B anyway. On the other hand, if you add it to website C, website C suddenly becomes more appealing than website A, right? And so website C is more sensitive to sort of local changes than website B. So, okay, if you make this assumption, how does this help you generate the data set? Well, we know that we've assumed that the predicted parameters will be close to the true parameters. So maybe to generate a realistic data set, all you have to do is sample points near the true parameter. And the way we do this is just add Gaussian noise to the true parameters. And we do this in 2 ways. One is we just add Gaussian noise to all the dimensions, which is like all the entries in the click-through rate matrix. The other way we do it is we keep everything constant and only change a few at a time, either 1 at a time or 2 at a time. Why do we do this? We think what we're trying to learn is how the decision loss changes with respect to predictions. This is similar to like a gradient or a Hessian of the decision loss with respect to the predictions. And so the way that you numerically calculate gradients and Hessians is you keep everything else constant, and then you just modify either 1 or 2 dimensions, and then you use that to calculate the gradient. Okay, so we use this to generate a bunch of data sets, right? And then, given that we have these data sets, what function of loss functions, what family of loss functions should we choose? We want something that's convex by construction, but also expressive enough to sort of model the decision loss, right? And so one thing we can do is we can take MSE, which is a standard prediction loss for regression tasks, which is this one is. And then what we can do is we can weight different sort of entries. So if the prediction for user 2, website C is more sensitive, then you can give it a higher weighting, right? And so that's weighted MSE. The second thing you can do is just use a neural network, because why not? But fundamentally, it's not convex. And so the question is, if convexity is not important, maybe this will do well, right? The last thing is essentially the quadratic loss function, right? And this is our most clever loss function. You learn a low-rank symmetric positive semi-definite matrix H such that the loss is a quadratic function of the predictions minus the true labels, right? And the reason this is clever is because this is equivalent to the second order Taylor series approximation of the decision loss when y hat is close to y. And so there is some sort of theoretical grounds for why this might be a good idea. Okay. I've hopefully told you what we're doing, why we're doing it. And the question now is, does it work? To answer that question, we're using the same sort of like example that we've used so far. And the answer is broadly yes, right? How do you read this? So on the right-hand side is how well a predictive model that's trained on a given loss function does. So we have two baselines. One is just mean squared error, like I said before. The other is decision-focused learning. And then are three sort of like families of loss functions trained on these sample data sets that we created. Now, all the results are normalized between 0 and 1. 0 is bad, 1 is good. And we find that our method does much better than the other baselines, so specifically our quadratic method does well. And something to note here is that the sort of not only that the expected value is high, but the variance is also low. And specifically what we find with DFL is that it does either well or badly. And the reason it does badly is because it reaches some sort of local optima. So the surrogate was not convex. And as a result, you landed in local optima, and that's why you did badly. And so the convexity is actually important. One other reason you might think that is because neural network does terribly, right? And that's not convex at all. And so convexity properties are obviously important. The second thing is we had a bunch of strategies. The results in the previous table are for all perturbed. But what we see is that for different families of loss functions, different sampling strategies actually work best. So specifically for weighted MSE, doing perturbing 2 at a time seems to be much better than perturbing everything all the time. In conclusion, we provide a method to easily learn task-specific surrogate losses for predict and optimize problems, but there's still work to be done. And to that end, I welcome questions from all of you. Thank you so much.